Hello viewers, continuing with our series on 3-dimension geometry, we will be discussing planes. We introduced you to the concept of plane in our earlier lesson. We learned that to form equation of a plane, you must know a vector, a direction which is perpendicular to the plane, called as the normal to the plane. We also learned two very specific forms which we will continue to make use of. Let us take a quick review of those two forms. One of them, the first form that you learned, was called normal form. So, what do we know of normal form? The normal form of plane uses what is referred to as the unit normal, n cap vector. We write the normal form of the plane as r dot n vector, which is the unit vector, equal to d. D is the perpendicular distance of origin from the plane. In Cartesian, this equation takes a look of Lx plus My plus Nz equal to d. This is a very specific form because you must know the unit normal and you must know the perpendicular distance of origin from the plane. Two very specific quantities that must be in a way ready-made handed over to you, which always does not happen to be the case. So, what is the other possibility? How else can you form equation of the plane? If you know a point that lies on the plane and a vector which is perpendicular to the plane, we come up with another form which looks like r minus a dot vector n equal to 0. Vector r is position vector of any point on the plane, vector a is the position vector of a known point, and of course, vector n is the normal to the plane. In Cartesian, this equation becomes a times x minus x1 plus b times y minus y1 plus c times z minus z1 equal to 0. A, B, C are the direction ratios of the normal, x1, y1, z1 are the coordinates of a known point of the plane. If you rewrite this equation, it gives rise to a linear equation in x, y and z. Today, our focus would be on planes passing through the intersection of two given planes. When two planes intersect, they intersect in a line, and through a line infinitely many planes can be drawn. So, in a way we will be discovering the family of planes which pass through intersection of two given planes. In this figure you can see a plane pi 1 and a pi 2 intersecting in a line, and through that line I need to figure out how to find equation of a plane, say pi 3. To begin with, if I know plane pi 1 and pi 2, their equations would look like r dot n1 vector equal to d1 and r dot vector n2 equal to d2, where n1 and n2 vectors are the normals to the given planes. Now, suppose I take a point which is lying on the line of intersection with the position vector t, then t must satisfy both the equations, that is t dot n1 vector must be equal to d1 and vector t dot vector n2 must also be equal to d2. In other words, if I take t1 dot n1 vector plus lambda, lambda could be any real number, times n2, it must be equal to d1 plus lambda times d2 for all real values of lambda. Since I am interested in finding the equation of the plane which passes through the intersection and t is any arbitrary point, t is a position vector of any arbitrary point on this line, this condition has to be satisfied by all points that lie on the line of intersection, and that gives rise to a locus which is nothing but the equation of the plane pi 3, which is stated as vector r dot n1 vector plus lambda times n2 vector equal to d1 plus lambda times d2. Lambda is a real number, any real number. So, as you vary lambda, you come across the entire family of planes passing through the intersection. In Cartesians, the same set of equations translate as given two planes with equations a1x plus b1y plus c1z plus d1 equal to 0 and a2x plus b2y plus c2z plus d2 equal to 0, the family of planes passing through the intersection are given as a1x plus b1y plus c1z plus d1 plus lambda times a2x plus b2y plus c2z plus d2 equal to 0. Now, if as we start with the exercises in a little moment, you will realize if I need a particular plane, I need a specific value of lambda, and to find that value of lambda, a certain other condition must be given to us to identify that particular member of the family of planes. Well, we will be taking the exercise shortly, but one more results which would come in handy, and that is about the angle between two planes. If two planes intersect, then what could be the angle between the two planes? If we take this picture, the two planes that are intersecting are making an angle depicted by that red angle as in the figure. We want to find the measure of this angle. We say that the two planes are inclined at an angle which is defined, can be calculated same as the angle between their normals. To understand this better, let us consider another figure. Here we have two planes 1 and 2 intersecting at an angle theta. So, how does this become the angle between the two normals? In this picture, as you can see, the normal n1 and n2. As you compare the angles which this vector n1 makes with n2, you will realize that it is nothing but 90 minus 90 minus theta, which of course is theta. And therefore, it is absolutely fine to understand and accept that the angle between two planes is defined as the angle between their normals. Another little thing that you must keep in mind is, if theta is the angle between the two planes, then so is 180 minus theta. We always consider the acute angle as the angle between the two planes. At the same time, if theta is now the angle which is between the two normals, then cos theta is same as the absolute value of n1 dot n2 by modulus n1 into modulus n2 vector, and therefore, theta will be nothing but cos inverse of this quantity. Also, note that two planes are perpendicular to each other if their normals are perpendicular to each other, which is same as saying that n1 dot n2 is equal to 0. And of course, two planes will be parallel to each other if their normals are parallel to each other, and therefore, this little condition comes in handy, knowing the normal of one plane giving rise to normal of another parallel plane. Now, keeping in mind the few things that we have discussed with us, I think you are ready for a small exercise. Here is our next question. It says, find the vector and Cartesian equation of the plane passing through the intersection of the planes 2x minus 3y plus z minus 4 equal to 0 and x minus y plus z plus 1 equal to 0 and perpendicular to the plane x plus 2y minus 3z plus 6 equal to 0. Knowing that given the Cartesian equations of the two planes, the family of planes passing through the intersection is same as a1x plus b1y plus c1z plus d1 plus lambda times a2x plus b2y plus c2z plus d2 equal to 0, we have the equation of the plane passing through the intersection of the two given planes same as 2x minus 3y plus z minus 4 plus lambda times x minus y plus z plus 1 equal to 0. If I rewrite this equation, it turns out to be 2 plus lambda times x minus 3 plus lambda times y plus 1 plus lambda times z minus 4 plus lambda equal to 0. This allows us to understand and identify what the direction ratios of its normal are. Now, keeping in mind that I have another plane given to us, that is x plus 2y minus 3z plus 6 equal to 0 with direction ratios 1, 2 and minus 3, which is perpendicular to the plane passing through the intersection, and therefore, the condition n1 dot n2 equal to 0 is applicable. So, if I take that into my consideration, I get a simple linear equation in lambda that gives us the value of lambda as minus 7/4. Substituting this value in the equation derived earlier, we get our required equation of the plane as x minus 5y minus 3z minus 23 equal to 0. Also remember that the question asks for the vector equation. So, you translate this equation into vector notation and it turns out to be same as r dot I cap minus 5 j cap minus 3 k cap equal to 23 as the required equation of the plane. Moving on, let us also look at how we find the angle between a line and a plane. So, we know that a line is intersecting a plane at a certain angle. How do we calculate this angle? Consider this picture and I think things will just fall into place. Here we have a line L defined along the vector B intersecting our given plane at a certain angle theta. The plane has a normal denoted by vector n. So, what do you see here? Is that making sense? The angle between the line and a plane is same as the complement of the angle between the line and normal to the plane. Isn't that so? So, the normal is perpendicular to the plane, line is making an angle theta and therefore, the angle between the vector n and the vector b is 90 minus theta. Therefore, if the theta is the angle between the line whose equation is vector r is equal to vector a plus lambda times vector b and plane's equation is vector r dot n vector equal to d, then automatically you will be able to see that we are only interested in not cos theta, but cos of 90 minus theta, which is nothing but sin theta, and that is the angle between the vector b and vector n, and that is equal to the absolute value of b dot n upon magnitude b magnitude n, and therefore, theta is same as sine inverse of the absolute value b dot n upon magnitude b magnitude n. Now, this result does come us in handy as we look at the applications where there is a concept of line combined with the plane. Line parallel to plane means line is perpendicular to the normal, right. Line perpendicular to the plane is same as saying or thinking of as line in the same direction as the normal to the plane. Little result, but will come in handy as we go along. Now, here is a problem for you. Find the foot of perpendicular from the point with position vector A given as I cap plus j cap plus 2 k cap to the plane with the equation r dot 2I minus 2j plus 4k plus 4 equal to 0. Hence, find the image of the point with respect to the plane mirror. Now, given the equation of the plane, I know the normal to the plane, and so in this case, if I am looking at a point A with coordinates 1, 1, 2 and from there I draw a perpendicular to the plane, we are interested in finding out the coordinates of point P. AP being perpendicular to the plane is parallel to the normal, and therefore, its direction ratios are same as that of normal. That gives us the equation of the line passing through the point A in the direction of the vector with direction ratios 2, -2 and 4. Therefore, P, which is any point on the plane, can be calculated as 2 lambda plus 1 minus 2 lambda plus 1, 4 lambda plus 2. This point P must lie on the plane. So, it must satisfy the equation of the plane. So, if I replace x, y, z with the coordinates of P, I get a linear equation in lambda, which is giving us the value of lambda as -12. With this value of lambda, we are able to find the coordinates of the point P. In order to find the image, the only thing that I need is an understanding that image is equidistant from the plane as the point A. So, foot of perpendicular P is the midpoint, and so if I take A dash as x dash, y dash, z dash, then using the section formula, I have a simple result which helps us to say that x dash plus 1 by 2 is 0, which gives me x dash as -1. Similarly, I have y dash and z dash. Using simple understanding of the image formed equidistant from the plane and A dash being perpendicular to the plane, we have the coordinates of the image as -1, 3, -2. I hope today's lesson has added to your understanding of a very important concept of 3-dimension coordinate geometry. We will see you in our next lesson.